Okay, my name is Ognjen Peković. I will present you this paper, Long-Term Structural Capacity Assessment of Industrial Steel Chimney. I think this paper should be in the other session regarding data-driven structural monitoring, but nevertheless. Okay. I'll try to be a bit brief because I'm the last one and don't want to take time from a lunch break. So why is it important to measure chimney thickness? Well, chimneys serve to take flue gases from the burner and take it to the atmosphere. So they are under influence of corrosion and erosion or abrasive action of flue gases, and high temperature, and also the chemical composition of the flue gases also accelerate corrosion. Then those are relatively thin structures, and stability and dynamic effects are also a problem. And local thinning can cause sudden failure, which happened quite a few times in the past. So it's important to measure the thickness regularly, and it's required by standards. So in this case, we have this chimney, which is 35 meter tall and 1.6 meter in diameter, composed of 6 sections. And as you can see, it was monitored for over 20 years, from 2005 to 2025. And the chimney itself was built around 1998, 1999. So it's a single flue duct. It serves as a chimney for a heating plant here in Belgrade. It takes flue gases from the gas-fired boilers. And also what you can see on the top is that during time, a lot of telecommunication operators' equipment is installed on the top of the chimney. So we had a task to see if the chimney can still function safely after this. During these 20 years of measurements, we acquired a lot of data through ultrasonic thickness measuring. The thickness was measured on different levels and different points around the circumference of the chimney. So here we can see that during those 20 years, 13 inspection runs were made, and total of 2,765 ultrasonic measurements were completed. I can see here are some measurements result. So as you can see, the problem was that not always the same people do the measurements. So the measurements are done on the different heights, also on the different points around the circumference. So we needed to do some statistical manipulation of results in order to have some meaningful results. Also, here in the first section, we can see that the standard deviation is quite larger than on the other sections. That's because in the first layer of the chimney, in the first 10 centimeters, where we had the deposits of flue gas condensate, that caused the little bit more corrosion and loss of material in the root section. This is maybe the better representation of our results. So we can see that around 1 to 2 millimeters of thickness was lost due to corrosion in this period over 20 years. So based on those results, we wanted to see if something unexpected will happen with the load-bearing capacity of this chimney. So we did finite element simulations in CATIA using parabolic elements, and we used the data mapping functionality to accurately map thickness on the chimney shell, and also to use because wind is the, how to say, main load in this case. So we used data mapping functionality also to simulate the wind effects. And if we can, here are tabulated results. Basically, we can see that all the results were as expected in some way. So we can see reduction in weight from 9,300 kilograms to 8,200. So roughly 15% of the weight of the chimney shell was lost. But that also caused around 10% increase in maximum stresses, displacement, and frequency. So actually, we didn't have anything unexpected to happen. And we can see that in this way, we are able to be sure that our chimney will be able to withstand those standard loads. And also, it is possible in this way to do some proactive maintenance, because chimneys are not maybe glamorous parts of the heating plant, but also a part that is required for a heating plant to function properly. So I hope that I was fast enough, and if you have any question, please ask.